Well, we won't bother waiting any longer. We'll just get started. We won't do class next week because that's spring break.
Yeah.
So I'm just going to keep spring break as spring break in my mind and not think that I'm doing some classes and not others. So next week's spring break, so we'll skip that class and continue the week after that as normal. Good?
Okay. Sounds good.
Okay. Maybe let's refresh ourselves a little bit on some of the concepts we talked about last time before we move on. Well, last time was probably still a lot of review for you guys. Just how do you multiply fractions together? How do you divide by fractions? Probably the hardest thing was the definition of absolute value. Remember the definition of absolute value? Mm-hmm. The absolute value of x is equal to, it's just x if x is greater than or equal to 0, and it's negative x if x is less than 0, right? Mm-hmm. So when I say the absolute value of 5, what's that equal to?
5.
Yeah, we come look, 5 is greater than or equal to 0, so we just spit out 5. We just spit out whatever symbol we put here. So that would just be 5. Looking at our definition of absolute value, what's the absolute value of negative 5 equal to?
5. Negative 5.
Negative 5.
That's 5.
So we're plugging in negative 5 for x here. Is negative 5 greater than or equal to 0? No. Is negative 5 less than 0? Yes. So we spit out negative x. If x was negative 5, then when we spit out negative x, that's the same as negative 5. Now it just so happens to be true that negative 5 is the same thing as 5, but it's important that you make the leap from here to here. Because here's where we finally lose kids galore. Let's say that a is some number less than 0. Some negative number. Then what's the absolute value of a?
A if it's greater than 0.
If a is some number less than 0, what is the absolute value of a?
Negative a.
It's negative a.
Yeah.
Right? We're plugging in a for x. If x is less than 0, we spit out negative x. A is less than 0, so we spit out negative a. So if a were negative 3, then the absolute value of negative 3 is negative 3. Or positive 3. Okay. Outside of that, I think most of the stuff we talked about last week should have been relatively straightforward review for us, right?
Yeah, it was.
We didn't have any questions on anything. Always and forever, you're welcome to look at the homework problems and bring any of those up in class and have us solve them in class if you want. Okay, so now we'll move on then with new material. So new material, the first definition that we're going to look at is one that you're already familiar with, but let's just make it explicit. And let's remind ourselves of a bunch of symbols. We remember how to read something like this. Let m, weird e, weird n. How do we read this?
Let m in real numbers, not real, natural numbers.
Within the natural numbers. Let m within the natural numbers, or let m be a natural number.
Yeah.
Remember what the natural numbers are? What are the naturals?
1 through 10. 1 through 10.
Now.
All positive.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, etc. Every positive integer. Make sense?
Yeah.
Okay. So let m be some positive integer. Let m be a natural number. Then a to the power of m, we define to be a times a times a times a times a times a times a m times.
Yep.
Pretty straightforward definition. All right. We have special names for when it's a to the power of 2. We call that a squared. And when it's a to the power of 3, we call that a
Cubed.
Why do we call it that? Anyone know why we call it that?
Cubed.
Why?
Because there's 3 dimensions.
On this one, let's start with this one. Why is this one called a squared? And then we'll get to a cubed.
Because there's 2, and then 2 dimensions, and then there's 3 dimensions with the cube.
But why would 2 dimensions mean that we call it squared?
Because a square is 2 dimensional.
It's the area of a square who has side lengths a. if I have a square with side lengths a, what's the area of the squared? Of the square? It's a squared. That's why we call it a squared. It gives us the area of a square. Furthermore, if I were to turn this into a cube with side lengths a, then the volume of the cube now is a times a times a, or in other words, a cubed. So that's where those names come from. Anyways, so, I don't know. I think you already get it, but let's just write out what a cubed is equal to then. So what's a cubed equal to? That's equal to a times a 3 times. Pretty straightforward? Alright, now let's do a proof. A to the m times a to the n is equal to a to the m plus n. Let's make sense of that really quick. If I have, really erase that. If I have 2 to the 3 times 2 to the 2, how many 2's do I have?
5.
I have 5 2's. I have, for this one, I have 2 times 2 times 2, and then for this one, I have 2 times 2, right? And so that's all together 2 to the 5. So we just added the exponents together. So when you multiply like terms, you add the exponents is a way that we commonly say that. So notice that we have an a here and an a here, but a is to one exponent, and this a is to another exponent. When we take the product of those two, it's the same as a to the m plus n. So we'll prove that real quick. By definition, a to the m, that's equal to a times a times a times a times a m times. And a to the n is equal to a times a times a times a times a n times. Right? So then, a to the m times a to the n is going to be equal to these a's times these a's. And how many a's do we have total? If we have m of them here, and we have n of them here, then altogether we have m plus n a's. Follow that? Pretty straightforward?
Yeah.
Good? Okay, more examples, I guess. So 3 cubed times 3 squared, that's the same as 3 times 3 times 3. Here's 3 cubed times 3 squared. And when you count them up, oh, there's 5 of them. 3 to the 5. This one, 2 to the 4, that's 2 times 2 times 2 times 2, 4 times, and we multiply that by 2 to the 3, which is 2 times 2 times 2, 3 times. Count them all up, you have 7 of them, 2 to the 7. Overstressing it?
I agree.
Okay. Next one. Next proof. This time we're going to prove, and I'll erase these examples to scribble right here. We're going to prove that a to the m to the n is equal to a to the m times n. Let's make sense of this one really quick. What am I saying? I'm saying that if I have something like, we'll do 5 squared, and then take that and cube it, how many 5's am I going to have when it's all said and done? 6 of them. So first off, let's do the cubed. So I have this thing cubed. That means we have this thing 3 times, right? So that's the same thing as 5 squared times 5 squared times 5 squared. Now we know how to do this, because those are all the same terms. So we just add the exponents. 2 plus 2 plus 2 is 6. So it was 5 to the 6, which is the same thing as 5 to the 2 times 3. So 5 to the 2 to the 3 was the same thing as 5 to the 2 times 3. That's what we're proving here. A to the m to the n is equal to a to the m times n. Make sense what we're proving? And it's going to be a pretty similar proof. By definition, a to the m to the n, when we have something to the n, that means we have that thing multiplied by itself n times. Right?
Yeah.
Then, by the proof we just did up here, that means that a to the m to the n is the same thing as, we can just add up all the exponents. So that's the same thing as a to the m plus dot 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 plus n. Right? And how many of these m's do we have?
N of them.
N of them. So m plus m plus m plus m plus m, n times is the same thing as n times m. You guys me? And then multiplication is commutative, so we can just flip the order. Good there?
Yeah.
Okay. Examples now. 2 cubed squared. So that's the same thing as 2, we don't need parentheses, that's the same thing as 2 cubed times 2 cubed, which is equal to, we know, just add the exponents together, 2 to the 6. 3 squared cubed is the same thing as 3 squared times 3 squared times 3 squared, which is equal to, add up the exponents, 3 to the 6. Any questions on those? Okay. Now, for some number a, where a is not equal to 0, so for some non-zero real number a, and for any two natural numbers, m and n, then we have these three statements are true. So first off, if a is not equal to 0, then a to the m over a to the m is going to be equal to 1. We just have a number, divided by itself. And we didn't divide by 0, because a is not 0.
Yeah.
Are those both m's?
Yeah, that's an m there, that's an m there. Good with that one?
Mm-hmm.
And then we have, if we have a to the m over a to the n, then that is equal to a to the m minus n, as long as m was greater than n. So if the exponent in the numerator is greater than the exponent in the denominator, then their quotient is equal to a to the m minus n. And if we flip it, if it happened to be that, I don't know what, I erase this. If it happened to be that n was greater than m, then a to the m over a to the n is instead 1 over n minus a to the n minus n. We'll prove this one, since these two are kind of the same thing. And this one seems like the more complicated of the two, but they both kind of follow with the exact same proof. So I'm going to prove this right-hand one. And shall a to the m over a to the n is equal to 1 over a to the n minus m, as long as n was a number bigger than m.
Okay.
Good? Alright, so that's what we're going to prove. So if a is not equal to 0, and n is a natural number greater than m, we're assuming a is a real number and n and m are natural numbers, then a to the m over a to the n is equal to 1 over a to the n minus n. That's what I'm going to prove. Okay, 1. Let a be any real number where a is not equal to 0, and let m and n be natural numbers where n is greater than n. Good so far? Mm-hmm. Okay. 2. Then a to the m over a to the n is equal to a to the m, that's the same thing as a times a times a times a times a, m times, right? So we have m of them up here. There's m. And in the denominator, we have a times a times a times a times a, n times. But since n is bigger than m, we're going to write out m of them before we finish writing out all n of them. So here's the first m of them, and then the remaining n minus m of them are right here. How many do I have total? If I have m a's here, and I have n minus m a's here, how many do I have total in the denominator? Am I losing you?
Yeah.
Two similar sounding words?
Yeah,
That's the problem? Alright, let's really quick replace m with 5 and n with 7. You with me? So a to the 5 over a to the 7 is the same thing as a times a times a times a times a, all over a times a times a times a times a times a times a. Here we have m a's. There's 5 of them. Here we also have m a's. There's 5 of them. Here we have n minus m a's. So how many a's do I have in the denominator total? 7, right? I have 5 here and 7 minus 5 here. So total I have 7. 5 plus 7 minus 5 is
2.
5 plus 7 minus 5 is
7.
7. We're back where we started.
Yeah.
We have a 5, we added 7, then we took away a 5. Okay, So now back up here, I have m a's here, and then I have n minus m a's here. How many a's do I have total? N. N a's total. There's m here, there's n minus m here. Add those two together and what do you get? N. That's some quick algebra. All right. So now we can cancel out the MA's up here with the MA's down here. So I can cancel out all these with all those, which just leaves me with these A's. And how many of these A's are there?
N minus n.
Yeah, so when we just write out those A's, that's the same as A to the n minus n. That's how many of these A's there were.
Okay.
Follow that? Real simple idea, but as you can see, the algebra can start looking dense pretty easily. And that's often a hard part with math classes when you first get into them. It's not that the ideas are so complicated that no one can grasp them. It's that the notation is so dense, it just takes a while to kind of sink in and to get used to seeing this kind of stuff. And so there's no real way around it except for to sit there, stare at it, think about it, and keep asking questions. And then you'll remember and forget and remember and forget. But if you were to go to in one of your other random classes, and if you were to start writing something like, there exists x in R such that x plus 2 equals 0. How many people would understand what you were writing right there? They'd be like, what's all this fancy stuff right here? Right? It's hard until you get it, then you're like, that's actually saying something real simple. It's saying there's a real number called -2. Right? So similar things happening here. It feels dense until you get used to this kind of notation, and then it just feels really simple after that. So if it feels like I'm overstressing an idea, it's because I know that that's possible. If suddenly you're all getting it, and now I don't need to keep explaining it, let me know. But because that can happen. It's really hard until it's really easy. It's like there's no middle ground. Okay, so now let's do some examples. A to the 5 over a to the 5 is equal to? 0.
Not 1.
Right? Take a number and divide it by itself. You think you should get a 1?
I don't know, maybe I'm just crazy.
Yes, it's a 1.
That's true, yeah.
Yeah. If you have 2 halves, what do you have? 1. If you have 3/3, 4/4, 5/5, a number divided by itself is just equal to 1. Or, coming back down to this here, a to the m over a to the m is equal to 1. Same thing, right? Okay, next. A to the 10 over a to the 2 is equal to?
A to the 8.
We got an a to the 5, we got an a to the 8.
Yeah, I'm going to say a to the 5.
We got another 5.
A to the 8.
And we got another to the 8. Which one will we write? 8.
Oh, yeah.
Subtraction.
If you have a to the m over a to the n, then that's equal to a to the m minus n, where the numerator was greater than the denominator. But we can also write this out pretty easily. A to the 10 over a to the 2, that's a times a 2, 3, 4, 5, 6, 7, 8, 9, 10 over a to the 2. 1, 2. That cancels out with that. That cancels out with that. How many are we left with? 8. Okay. It's hard till it's obvious, and it's easy, right? Okay. A to the 4 over a to the 7 is equal to?
1 over a to the 3.
1 over a to the 3? What kind of nonsense is that? You guys just going to eat that up? Or can someone correct him?
Negative?
-3?
No.
No? Maybe don't look at me and look at what we proved. Or we can write it out. 1, 2, 3, 4 over 1, 2, 3, 4, 5, 6, 7. Okay, that cancels with that, that cancels with that, that cancels with that, that cancels with that. What are we left with?
A to the 3.
1 over a to the 3. Right? Yeah, don't let me trick you just because of how I say something. Ignore me, just think what makes sense. Stick with that. I'm a liar. But the math can't lie. All right? Let's try another one. 3/2 to the 4.
3/2 to the 4 either way, just without the parentheses.
Do you want us to
What
find the
kind of
number?
answer
Yeah,
are
you're
you
trying
looking
to
for?
look for the number 6.
Well, sure, you can give me the number.
6.
It's not too bad.
Number 6.
What is 3/2 to the 4? That's 3/2 times 3/2 times 3/2 times 3/2, right?
Yeah.
So that's the same thing as 3 to the 4 over 2 to the 4,
Yeah.
right? Which is equal to
81 over 16.
81 over 16. Oh, come on, you can do 3 times 3 times 3 times 3 in your head. What's 3 times 3? 9 times 3, 27 times 3. 60 plus 21, 81. Okay, 81. You better for sure be able to do that. 2 times 2 times 2 times 2. You can do that in your head. Yeah, don't rely too much on calculators. They'll come back to bite you. Because you'll make mistakes plugging in numbers. That's what's going to happen. So, it's very, very, very useful to train yourself to be able to do easy arithmetic in your head quickly. It's one of the ways that we quickly check to make sure we didn't make a mistake in a calculator. Give you a quick example of that. If I were plugging into my calculator, maybe I don't know it off the top of my head, 17 times 17. So I plug that into the calculator and it spits out something like 449. Is that 17 times 17?
No.
How do you know? Well, even if you don't know 17 times 17 in your head, so we're wondering, is 17 squared equal to that? Maybe you don't know that in your head, but you know in your head that 20 squared is equal to what?
400.
400. So can 17 squared possibly be 449? No. So that's how you do sanity checks. I plug in 17 squared into my calculator, and I'm wondering, does that answer make sense? Well, I know this, so no, I must have made a mistake. Now, obviously, we don't really do that with our calculators, but with more complicated problems, when you get to some real math classes, some more rigorous math classes, then what you plug into your calculator, it's very possible you make mistakes. And in physics, we make mistakes all the time. The only way we catch them is we think, does that make any sense? Because a lot of times it doesn't. So, don't be lazy. Just think it through. See if you can come up with the answer. All right, so what was the answer here?
81 over 16.
81 over 16?
Yes, sir. I believe so.
You believe so?
That's what it was.
Okay. Next, let's do this one. That seems a bit daunting. We can always just write it out. We have 4cd squared over 3x times 4cd squared over 3x, right? How do we multiply fractions together? We multiply denominator by denominator, numerator by numerator.
Yeah.
What's 3x times 3x?
9x squared.
9x squared, right?
Yeah.
And 4 times 4?
16.
16. Or 4 squared if we want. C times C?
C squared.
C squared. D squared times D squared?
D to the 4.
D to the 4. Just adding up all their exponents. You can think about C as having an exponent of 1 if you want. 1 plus 1 is 2. 2 plus 2 is 4. And we had 4 to the 1 plus 4 to the 1 gives us 4 squared. Or 16. Good? Okay. So, this was equal to, when we square it out, we can just square, what we just saw is we can just square each term. 4 squared is 16, c squared is c squared, d squared is d squared squared is d to the 4 over 9x squared. Just apply the square to each term in there and you're fine. Make sense? Okay. Let's try another one. What's this one equal to?
9 plus 225.
9 plus 225?
No, just 225. I also said minus. 50 times 15 is 225, right?
15 times 15 is 225. Not sure where you're going with this.
Yeah, that's not all squared. Never mind.
We're just rewriting this term.
Just cross out the a's and x's.
So just tell me what to write.
Is that negative 15?
Oh, yeah. I know you can't make your way all the way up to the front row. That leg. It's one thing to walk from your home to here.
That's a good front row.
Yeah. Gotta draw a line somewhere. So, yeah, that's a negative 15, that's a 10, that's an a cubed, that's an a, that's an x to the 5, that's an x to the 9.
Negative 15 times a squared over 10 times x to the power 4. Yeah.
What did he do here? He canceled out this a with one of those a's, so now there's only 2 a's left instead of 3. And he canceled out 5 of these x's with 5 of those x's, leaving 4 of those x's. Everyone follow that? All right, is that it?
Sure hope so. You can subtract or simplify the 15 and 10.
Yeah, I can also write this as negative 3 times 5 times a squared over 2 times 5 times x to the 4, which is equal to 5's cancel out.
Yeah.
Right? So it's negative 3a squared over 2x to the 4. And we can put the negative with the numerator, or we can put it out front. We saw that from last time. Putting your minus out front and putting it in the numerator, same thing. Does it make sense why? Let's make sure it makes sense why. If I have negative x over y, then that's the same thing as negative 1 times x over y, right?
Yeah.
Which is the same thing as negative 1 over 1 times x over y,
Yeah.
which is the same thing as negative x over y. So negative x over y is the same thing as negative x over y. Everyone follow that?
So if there's a fraction in the denominator, what do you do?
Huh?
If there's a fraction in the denominator, does that ever happen?
A fraction in the denominator? Or a negative in the denominator?
Negative in the denominator.
Okay. We can write negative 1 as 1 divided by negative 1. Which then puts the negative right there.
So you can put it in either.
Yeah. It's just as a matter of convention, we keep it in the top.
Yeah.
But yeah, 1 divided by negative 1 is negative 1 is negative 1 divided by 1.
Yeah.
Does that make sense? Hope so. Okay. Because negative 1 times what gives us 1?
Negative 1.
Negative 1. So 1 divided by negative 1 is negative 1. Okay. Anyways, where did we leave off? So we did this example. Okay, so we're right here. Now notice that so far we only had this defined for where m was a natural number. Or in other words, where m was 1, 2, 3, 4, 5, etc. Right? What about when it's 0? Well, we define a to the power of 0 to always be equal to 1 where a is not equal to 0. That's our definition. And that definition behaves very nicely with the rules we already established. For example, if I have a to the n times a to the 0, we know that we can add the exponent, right? So that's the same as a to the n plus 0. What's n plus 0? N. So that's the same thing as a to the n. So when I took a to the n and I multiplied it by a to the 0, I still got a to the n. So a to the 0 behaves the same way as 1. A to the n times 1 is a to the n.
But a to the 0 says that the exponent tells you how many a's there are, and if there's 0 a's, then there's no number. But you can still write 0.
It's an empty product. An empty product we define to be 1. I don't know if you've come across factorial before, but it's the same reason we call 0 factorial equal to 1, and we don't call it equal to 0. You haven't come across factorial before?
Nope.
Okay, never mind then. Intuition. Why do we want an empty product to be 1? Let's say that you, me, and Jeremy are trying to multiply a bunch of numbers together. Now, one way that we could do that is I could multiply all my numbers together, Jeremy can multiply all his numbers together, you can multiply all your numbers together, and then we could just multiply those 3 numbers together, right?
Yeah.
So if we were trying to multiply the numbers 2 times 3 times 4 times 5 times 6 times 7, I could say, you take these 2, multiply those together, I'll take these 2 and multiply these 2 together, Jeremy will take these 2 and multiply these 2 together, then take our answers, multiply those together, and that gives us the total answer, right? Well, what if instead we say, okay, I'm going to do these 3, Jeremy's going to do these 3, and you do these ones. So your job is to do an empty product. If you spit out 0, then that gives us our total product is 0. If you spit out 1, you don't change our product.
Does there have to be an empty product?
Well, that's what we gave you.
That's what you were given. If you're some function that's supposed to spit out products of numbers, and we give you no numbers, then we want you to spit out 1. The product that doesn't change anything.
Yeah.
Because remember, multiplying by 1 and adding 0 are roughly the same thing. If we were adding a bunch of numbers up, and we didn't give you any numbers to add up, we want you to spit out 0. If we are multiplying a bunch of numbers together, and we don't give you any numbers multiplied together, we want you to spit out 1. And so that's why we define the empty product to be 1.
Yeah.
That's just intuition. Okay, so a to the 0 we define to be 1. And it behaves nicely with our rules. We already showed how it behaves nicely here. Here's another way it behaves nicely. A to the n, we know that 1 is equal to a to the n over a to the n, right? Same number divided by itself, right?
Yeah.
And we also know that when we have a to the n over a to the n, we can represent that as a difference, a to the n minus n. What's n minus n? 0. So that's the same thing as a to 0. So once again, we get a to 0 equals 1 using the rules that we have. Good?
Yep.
Okay. So that's it for exponents so far. We'll do more with exponents later on. But we'll leave it there for now. Next concept we're going to move on to is sets. Now, unfortunately, I've already been throwing sets at you left and right without even thinking about telling you what a set is. Sorry about that. And so now we'll explicitly talk about what a set is. Now, because you can't define everything in mathematics, technically a set doesn't have a definition. Technically, it's one of the things that you just start out with. You can't define a set the same way that you don't define a point in geometry. But we give you intuition for what a set is. Intuition for a set. It is any unordered, unique collection. Unordered, meaning order doesn't matter. Unique, meaning duplicates don't matter. Any unordered, unique collection. And typically when we write a set, we write the members of a set between 2 curly brackets. So I write this curly bracket means I'm starting a set. Then I write 1, 2, 3, then I do end curly bracket. This is a set containing the members 1, 2, and 3.
Does the set have to include numbers?
No. I could also do a set containing 1, 2, square, smiley face, and pi. That's a valid set. It's just a set containing any collection. Doesn't matter what you stick in there. You can turn square into SpongeBob. We're still good. Still a set. Anything can be in there. Now, since it's an unordered unique collection, that means that the set containing 1, 2, 3 is equal to the set containing 3, 2, 1. Because order doesn't matter. So this set is the same as this set.
Yep.
And since duplicates don't matter, since it's a unique collection, meaning duplicates don't matter, the set containing 3, 2, 1 is also a set containing 1, 1, 2, and 3.
Okay.
They have the same elements. They both contain 1, they both contain 2, they both contain 3. Therefore, they're the same set.
Okay.
Good? And now we've already been talking about a bunch of sets. But here's some common sets. First off, there's this set. We call this the empty set. That's shorthand for the empty set. So the empty set is equal to the set containing nothing. Open curly brace, close curly brace. What's in there? Nothing.
Why do you need that?
It's absurdly useful.
Okay.
The empty set acts a lot like 0 does in arithmetic. So the way that 0 is super useful in arithmetic, this is super useful in working with sets.
Why wouldn't it be 1? Because there's no product. There's no number.
There's nothing multiplying.
Look. Should we say this? Yeah, we'll say it. All mathematics is technically, you can technically build it up from set theory. Now, I told you, we started out with our axioms, which we just said, these are our axioms and we're just going to give them to you. And you're just going to accept those as true and work from there. But if we were teaching a class called set theory, we actually start with the axioms of set theory and we construct the axioms that we started with on the real numbers. So those aren't really our starting place. We just started there because we got to start somewhere, and I can't build everything up from you from ground zero, otherwise we get 5 classes before we could even start this class. 5 other classes. Well, not 5, but we'd have to do logic, we'd have to do set theory, maybe a little bit of a real analysis course, then we'd be ready to go. So like 3 courses to get started, and we don't have time to do that. So we just start with the axioms and work from there and just work with intuition. But if we went back and we started with set theory, then our definition for the number 0 would actually be the empty set. And that's the definition for 0. And the definition for 1 is the set containing the empty set, which is this. And that would have been our definition for 1. And our definition for 2 would have been the set containing 1 and 0. Sorry, this is a set containing 0. 2 is the set containing 1 and 0, which would look like this. Put a comma there.
Is there supposed to be 5?
And I won't... Huh?
There's supposed to be 5 and 3? Oh, never mind. Okay, I get it.
You see how they pair with each other?
Yeah.
And notice, how many things are inside this set?
0?
No, there's this thing.
Which is 0?
Here's where the set starts. Then there's this thing. Here's where the set ends.
So there's 2 sets.
So how many things are inside of here? How many things are inside this set?
There's 1 set inside that set.
So there's one thing in there.
Yeah.
So notice that there's one thing in here. One thing in here. Look at how many things are inside this set. We have this thing, comma, this thing.
And then the thing inside that. Oh, that thing inside that thing is that thing. Okay.
So now there's 2 things inside this set.
Yeah.
And we would similarly define 3 as a set containing 2, 1, and 0. And it would turn out it has 3 things inside of it. And so it's the fact that the count of the number of things inside of there is what gives us those numeric properties that we like. If we were constructing from ground zero. So technically, you start out with set theory and you construct numbers using sets.
So the only reason that makes sense is because it's the definition of...
It's just a definition. We got to start with something. We start with the empty set. Okay, there's our start. Now, that's the only thing that we use to construct 1. What's 1? Well, it's a set containing the empty set. What's 2? Well, it's the set containing the set containing the set containing the empty set together with the set, or the empty set. Really easy to get confused in what I'm saying, but I think when I draw it out, it makes perfect sense.
Yeah.
So the empty set is very basic to mathematics. Very, very fundamental. More fundamental than a concept like the number 1. Anyways, quite a tangent there. Okay, so the empty set. That's a common set. It's a set containing nothing.
Yeah.
Then another common set is this set. That n. What's n?
Natural.
It's a set of natural numbers. 1, 2, 3, 4, ... means continue in this pattern forever. Right?
Mm-hmm.
And then we have this z. What's the z?
Integers.
Integers. So to write out the integers, we do ... comma, -2, comma, -1, comma, 0, comma, 1, comma, 2, comma, ... Follow this pattern forever that way and that way.
Mm-hmm.
There's the integers. What's this q?
Rational numbers.
Q is a set of all rationals. That's the set of all possible fractions you can write. So this has inside of it 3 halves, 2 19ths, 61, 2,542, and obviously we can't write everything in there. There's an infinite number of things in there.
Yeah.
Right? And then we have the R. What's the R there? The set of all real numbers, R, which is pretty much what you currently think about as a real number, unless you know what complex number is.
So could you say that each of those sets include the same amount of numbers because they're all infinity?
No. Now, first off, this set contains no numbers.
Well, except the...
Now, the natural numbers, the integers, and the rationals all contain the same amount of numbers. They all have the same cardinality, the same size,
Infinity.
which is a type of infinity. The real numbers is bigger, though.
You know how you showed how natural numbers and integers, you can do it as the formula, if x is a positive, then do this, and if x is a negative.
Yeah, I can create a bijection,
Compare.
a one-to-one function, from the naturals to the integers, pairing every natural to one and only one integer.
Can you prove that you can't do that with the real numbers
Yes.
on the board?
Yes. Yes. We'd have to write some things out, but yes, we could do it. It'd take like 15 minutes. Maybe 10. But yeah, we could. So we can do that at the end of class if you want. Okay, so put a pin in that question. Once we cover this, we'll come back and talk about that to your heart's content. Okay, so there's some common sense. Now we have this notation, which I've already used 100 times, but now we'll write it out. When I say x is a member of A, that means x is an element or a member of some set A. It just says x is in the set. So 2 is in the set containing 1 and 2. Square is in the set containing 1, square, and 2. 3 is not in the set containing 1 and 2. Good? Okay, then we have a notion of set builder notation. This is a way for us to define useful sets. So, with set builder notation, what do? We typically put some dummy variable, colon, and then some condition that dummy variable satisfies. And so then it's a set of all the things that satisfy some condition. So let's give you an example. One way that I can define the natural numbers. I can say the natural numbers is a set of all m, where m is an integer and m is greater than or equal to 1.
Okay.
So if m is an integer and m is greater than or equal to 1, m is a natural number. So what are the natural numbers? It's a set of all m such that m is an integer and m is greater than or equal to 1. Make sense? Dummy variable, condition. The condition is it has to be an integer and it has to be greater than or equal to 1. Good so far? Now it's also very common that if our dummy variable comes from some other set, we usually write that on the left-hand side of the colon. This is a perfectly valid way to write it. This is a more common way to write it. So writing the exact same thing again, what are the natural numbers? It's a set of all integers such that the integer is greater than or equal to 1. It's a set of all integers m such that m is greater than or equal to 1. Same thing.
I don't get how it is the same thing.
This and this.
Yeah.
This is a set of all m, where m is an integer and m is greater than or equal to 1.
Yeah.
This is a set of all integers m, where m is greater than or equal to 1.
Oh, okay. Yeah, I get it.
So when, in your condition, the first thing you do is specify a set that that your dummy variable has to belong to, we typically just put that first. There's nothing wrong with this, it's just you'll probably see this a lot more. Make sense?
Where's the kind of places that you'd see this?
You saw us all over the place in your calculus textbook, remember it or not. Maybe not so much with the calculus textbook, because it was understood that we were always working with the real numbers. So we didn't have to specify, but you have to specify more in like a discrete math class, because sometimes you're coming from the rationals, sometimes you're coming from the integers, sometimes you're coming from the naturals. So it's fairly common. It's one of those things that you don't really notice unless you have to notice it. Unless the teacher makes you pay attention to it. Because you can kind of just get what's saying. Okay, let's write another one. What if I want to write the set of all evens? Of all the even integers? Well, that's a set of all integers m, where 2 divides m, or m is divisible by 2. You might not be used to that operator, common operator. Not one we'll work with in this class, but 2 divides m just means 2 goes into m evenly. Good? Just giving you examples of set builder notation. We don't really care about that operation, just examples. Okay, now let's talk about the rationals. Let's actually write out the rationals now. What are the rationals? The rationals are the set of all real numbers where there exist two integers m and n, where n is not equal to 0 and x is equal to m over n. Kind of a mouthful, but let's say it again. First off, intuitively, what's a rational number? It's just a fraction. If you can write it as a quotient of two integers, it's rational. 6 over 13, rational. So, a real number x is rational, provided that there exist two integers, m and n, such that x is equal to m over n, and that n was not 0. So x equals two integers over each other, where the bottom one isn't 0. That means it's rational. So it's a real number that can be expressed that way. Good?
How would you define integers?
Well, these weren't really definitions. These were just other ways of writing them.
Or yeah, how would you do that to an integer?
How would I write the integers? We could write that as something like, we could write it in terms of the naturals pretty easily. I can say the integers is a set of all, I don't know, m, such that m is a natural number, or negative m is a natural number. So let's take 5 for example. Is 5 in here? Let's see, is 5 in the natural numbers? Okay, so it's in here. Let's look at negative 5. Is negative 5 a natural number? No. Is negative 5 a natural number?
Yeah.
Yeah. So we have negative 5 was an n, or its negative was an n. And so that would give you all the integers.
So these are not definitions.
No, these are not definitions. This is just getting you comfortable with set builder notation. So I'm just rewriting out some sets using set builder notation. Okay. Now, a variable. Again, we've been using variables left and right. Let's nail down exactly what a variable is now. Definitions can sound a bit weird, but your intuition for a variable is most likely already right. What's a variable? A variable is a symbol, such as x, which may represent any particular element of a non-empty set S. We call S the domain of the variable x, and we call each member of S a value of x. Okay, that could have been a mouthful, right? So, I have an example down here. And then we'll use this example to make the definition make sense. So let's look at this example. Let S be the set of all real numbers less than 2. You with me? So all the real numbers less than 2. So now when I say that the variable x is less than 2, that is identical with saying that x is a member of S. So S is a set of everything less than 2. Saying that x is less than 2 is saying that x is some member of S.
Yes.
Which member, we don't know. It's a variable.
Okay.
There's multiple possible values that x could be, since S has multiple members. All we know that x being less than 2 says the same thing as x is a member of S, where S is a set of everything less than 2. That's what we mean by variable. So now let's read the definition again. Again, this is really dense, but you already have great intuition for what a variable is. So just need to connect it with the actual definition. So a variable is a symbol, such as x, which may represent any particular element of a non-empty set S. Good? Anything weird about that? And then we call S the domain of the variable x. So x less than 2, what's the domain of x? It's that set, S. It's all the possible values x could have. Make sense? Okay. A lot of terminology, but pretty straightforward once you get it. Okay, a constant. What's a constant? A constant is a symbol, such as a little a there, something, representing a fixed number. So a constant represents a fixed number. A variable represents some element of a set. So a variable could be one of any number of values. A constant is always one and only value. It's a fixed value.
And are constants usually capitalized or no?
No, as a general rule, we use A, B, and C when we're talking about constants. And as a general rule, we use X, Y, and Z when we're talking about variables. So if you were to see something like ax squared plus bx plus c equals 0, which you've probably seen 100 times,
Okay.
it was understood in this formula that a, b, and c were constants and that x was a variable. That was just understood. But that's just because we're falling in love with a certain notation that we get used to. Nothing special about those letters. It's just by convention, that's how we use it. And there's tons of exceptions to the rules. If you ever take physics, you'll use pretty much any letter for a variable at some point. And when you run through the letters, you'll just start using the Greek letters. And then you'll even use the same letters for different variables. V means one thing in one context and another thing in another. Anyways. So it's just a convention. And you can often infer from context what's a constant, what's a variable. So let's look at a common formula that hopefully you've seen. A is equal to pi r squared. Where have you seen that before?
It's like Greek
Circumference of a circle.
Surface. Okay. Area of a circle. We usually talk about surface area if it's a three-dimensional object.
Well, I was thinking like cylinder, and that's the surface area.
Yeah.
Area of a circle. Come on.
I was close.
What do you mean? You said something like circumference.
I said diameter.
You said diameter. Here's why you're way off. Diameter is measured in terms of meters.
I know.
This is going to be in meters squared. It has to be an area. Right? So the area of something, in this case it's the area of a circle.
Why does diameter have to be in meters?
Well, the point is it's one-dimensional. And whatever comes out of here is going to be two-dimensional.
Oh,
Right? If r is 3 meters, when you plug that in, then you're going to get 9 pi meters squared, which has to be talking about an area, because it's meters squared.
Obviously.
Right?
Yeah.
So even if you don't know it right off the top of your head, if I say which one of these gives the volume of a circle, and I say 4/3 pi r cubed, or 2/3 pi r to the 4, you instantly know it can't be that one. R to the 4, that's not a volume. R to the 3 is a volume. So maybe it's this one, or maybe I just lied to you and the formula's not up here. But it's definitely not this one.
yeah.
Right? Okay, area of a circle. I don't know. Just needed something simple that has variables and constants in it. So in here, what's what? Tell me which ones are variables and which ones are constants.
Pi is a constant.
Pi is a constant.
Yes.
You agree with that?
Yes.
That's a constant. Maybe you don't understand what this formula is saying. R represents the radius of a circle.
Yep.
So if I take some circle with radius, and it has a radius of 3 inches, then what's the area of the circle? Then the area of the circle is going to be 9 pi inches squared. That's what it's saying.
Which means pi and r constants.
And A is a constant.
Which means which and which are constants?
All of them are constants.
Everything's a constant?
Yeah.
Yeah, that's what
Okay,
it says.
no.
Is 2 a variable?
This one is constant, that's a variable, and that's a variable.
Why is R variable?
Those depend on what circle we're talking about.
Yeah.
R was 3.
Pi never depends on what circle you're talking about. I drew a particular circle, but this formula doesn't just apply for circles where your radius is 3. It also works when your radius is 4. It also works when your radius is 5.
Oh, that's what you're saying.
It doesn't work for 6, but if you go to 7, it works again.
So variables when it...
No, it does work for 6. Don't listen to me, look at the math. Well, we didn't really prove this, so you can't look at the math. So maybe we shouldn't lie about this one. But no, so variable, variable, constant.
And then 2.
These two depend on what circle you're talking about.
Yeah.
This is referencing one and only one number.
And then 2 is a constant too.
Oh, and 2 is a constant. Sure.
Okay.
Good?
Yep.
And you've even heard some of this terminology before. They call R the independent variable, and they call A the dependent variable.
Or X and Y.
Or, yeah, you could also represent this as y is equal to pi times x squared, where x is your radius and y is your area.
Yeah.
Similar thing. Nothing special about A and R here. We could have just as easily used y and x. It's just, we like to use A's for areas and R's for radiuses, because it works.
Crazy.
What's that?
So it's crazy how...
Yeah,
it
it's
works.
just like how we use L for angular momentum.
We use that for lane.
We also use it for angular momentum.
Just normal momentum.
And yeah, P for normal momentum.
Oh, it's also for pressure. And
Yeah,
then
for
they've got
pressure.
Rho, which is just, it's a P. without
Rho, yeah, well that's density.
I think I kept getting problems wrong because I couldn't figure out the Rho and pressure difference on the formulas.
That'll get you. Okay. Anyways, so think you have some good intuition for variable versus constant, what the difference is?
Yes, sir.
Yeah. Well, if Celeste is good, then we're all good, right?
That's right.
Let's see. I'll just move it again. I'm gonna go to the whiteboard. Okay. So next section in the book was on polynomials, and so we're into polynomials. But before we define a polynomial, first we want to define a monomial. Monomial. Mon often means one.
Yep.
And then poly means
Multiple.
many. Typically many. Not necessarily a plethora.
Plethora just means multiple.
Well, it means an abundance.
Yeah. Maybe the 2 is abundant.
It could be abundant. Yeah. A lot of bigness there. Anyways, a monomial is a dense definition, but then we'll do an example. I think you'll be pretty clear what it is. So first we'll read the definition, then do an example, then go back to the definition. So a non-zero coefficient, remember what the coefficient was?
Yep.
It's the thing that came in front of the variable. So a non-zero coefficient multiplied by some variables, maybe multiple, maybe just one, but some variables to some non-negative exponent.
Isn't a variable what makes it a coefficient? Or is it a coefficient and a variable?
2 could be a coefficient. Alright, so that's what a monomial is. And the degree of a monomial is the sum of the variable's exponents.
Yep.
So now let's look at some examples and then go back to that. So let A, B, and C be constants, and X, Y, and Z be variables. Good with me so far? Okay, so let's look at this term right here. 7ax squared y cubed. First off, what's the coefficient?
7.
7a.
7.
Everything that's not the variable part.
Oh yeah, so that's constant. Yeah.
You with me? Is 7a 0?
Could be.
Could be. We'll assume that a, b, and c not equal to 0. Okay, so is our coefficient 0?
No.
No. So we have a non-zero coefficient multiplied by some variables, here's some variables, to some non-negative exponent. Non-negative exponent, non-negative exponent. What's the degree of this monomial?
3. 5.
5. It's the sum of the exponents of the variables. That's a 5th degree monomial.
But those are different variables.
It has multiple variables in it, that's fine.
There's one term.
It has 2 variables. This is one term. There's its coefficient, there's its variables. The variables are to some non-negative power. Add up the exponents. That's the degree of that monomial. Good?
I think so.
Okay. I mean, it's a pretty straightforward definition. Non-zero coefficient with some number of variables, doesn't matter how many you want, to some non-negative exponents. And when we say non-negative exponents, we mean 0 or a positive integer. We don't mean, I can't replace 3 there with 3 halves. If I were to put 3 halves here, this is no longer a monomial.
Because it has to be.
When I said non-negative, I meant 0 or a positive integer. So I meant to say some non-negative integer
Okay.
exponents. Good?
Yeah.
So this one is a 5th degree
Why
monomial.
couldn't it be a fraction?
Huh?
Why couldn't it be a fraction?
It's just by definition.
Okay.
There's nothing broken about the term if it has a fraction there. It's just no longer a monomial.
Okay.
Okay, let's look at another one. What's my coefficient?
13 pi.
13 pi is my coefficient. And x, z, and y are my variables, right?
Mm-hmm.
And what is the degree of this monomial?
6.
6? When you add up the exponents, so you get 5?
No.
Who thinks 6? Because y without an exponent is the same thing as y to the 1.
Yeah.
What's y to the 1 is just y. So when you have it by itself, it's implied that there's just a 1 there. And now 3 plus 2 plus 1 is 6. So yes, it's a 6th degree term. Make sense?
Yep.
Okay. Oh, now let's look at this beast. 9. What do you think? Is that a monomial?
Yeah.
Yes, sir.
It is?
Yep.
Is this a non-zero coefficient?
Uh-huh.
Followed by some number of variables?
Possibly.
Yeah.
Times 0a.
Yeah?
Mm-hmm.
Who thinks that this is a monomial? It is, and here's how we know. Because I can write this as the same thing as 9 times x to the 0.
Oh yeah.
Now, coefficient times a variable to a non-negative integer exponent. So since we just said non-negative rather than positive integer exponent, if I would have said positive integer exponent, this would no longer count. But since we just said non-negative integer exponent, this 9 now counts. So all constants
Oh yeah. 0.
are monomials. And you can rewrite it this way. This is identical with this, which is for sure a monomial. So since that is, and this is identical with that, that has to be 2. So the same thing. Does that one make sense? What's the degree of that monomial?
0.
It's a 0th degree monomial.
0.
0th. I don't know.
0.
Why is it not 1?
0.
A 1st degree one?
Yeah.
Because when I add up the exponents, what do I get?
X.
Well, does 9 have an exponent of 1?
You add up the exponents of the variables.
Oh.
Because 9 has an exponent of whatever I want.
Mm-hmm.
I can say, is that 9 to the 1 or is that 3 to the 2? Or is that the square root of 3 to the 4? Etc. So in determining the degree, we only look at the exponents of the variables. and we add them up. Okay, think you understand what a monomial is?
Yep.
Alright, so now what is a polynomial? A polynomial is just a sum of monomials. Take some number of monomials, maybe 1, maybe 2, maybe 10, add them all up, what do you get? A polynomial.
Yeah.
What if we add up nothing? Is that a monomial?
Yes, the first one. Monomial.
We have a yes, we have a no. What do we think, girls?
It's a monomial, not a polynomial.
Well, we could rewrite this as 0 times x to the 0, right?
So now,
So, is it a non-zero coefficient multiple? Ah! Yeah, it helps to read the second word of the definition. Non-zero. No, this is not. So it's not a monomial, it's not a polynomial.
it's just
Every monomial is a polynomial. So this is also a polynomial, this is also a polynomial.
okay.
It's just, we're summing up one terms,
Oh, okay.
which is fine. Good? Now, the degree of a polynomial is the highest degree of its component monomials. So look at all its monomial terms, figure out their degree. Whichever one has the highest degree is a degree of the whole polynomial. Does that make sense? So, before we do more with that, we have some special names for some special type of polynomials. If we have a polynomial with just 2 terms in it, if it's just 2 monomials added together, we call that a binomial. If it's 3 terms added together, we call that a trinomial. Good so far?
Yeah.
And then, if a polynomial is a first degree polynomial, which means the highest exponent to the variables is 1, then we call it linear. So a first degree polynomial is said to be linear. So there's some terminology. Now let's look at a couple examples and make sense out of it. So this right here, we have 5a plus 3x cubed y squared plus 17a to the 9. Is this a polynomial?
Yeah.
That's a monomial, that's a monomial, that's a monomial. It's a sum of monomials, therefore it's a polynomial. How many terms does it have? How many monomials do we add up?
3.
3. So this is also called a trinomial. A trinomial is a polynomial with 3 terms in it. What's the degree of this thing?
9.
Anyone have a different answer?
Yeah,
What's the degree of this term?
1.
0. A is a constant.
Oh.
It's not a variable.
Oh.
So this is the same thing as 5 times a times x to the 0.
Okay.
So this is the 0th degree. This one is
5.
5th degree. This one is
0.
0. What's the biggest out of 0, 5, and 0? 5. So the whole polynomial is a 5th degree polynomial.
Yes, sir.
Make sense? Okay. Now let's look at this one. Bx. Is that a monomial?
Yeah.
C. Is that a monomial?
Yeah.
Okay. So it's monomial composed of 2 terms. We call that a binomial. What's the degree of this term?
1.
What's the degree of this term?
0.
So what's the degree of the whole polynomial?
Linear.
1. So since the degree of the whole polynomial is 1, this is called a linear polynomial. And you might notice something nice about linear polynomials. What do we use them for?
Slope. Or
Linear equations or functions.
Linear equations, linear functions. Equations of lines. Linear. And we'll see that for those of you who haven't seen that already, but hopefully they're used to equations of the form y is equal to bx plus c. General equation of a line.
V. X plus
Yeah.
V.
b x plus c.
Yeah, we're used to n x plus
general form. That's just a point slope, or slope intercept form. But we'll get to more of that later, in case that's running out. Okay, so there we go. Tell me those. Now we're moving on to square roots. Square root. So x is said to be a square root of a. I should have used a. Let me replace a's with b's so that it's obvious when we're talking about the word and when we're talking about the letter. Sorry, I should have thought ahead. Alright, so let's try it again. X is said to be a square root of b, provided that x squared is equal to b. If x squared is equal to b, then x is a square root of b.
Yep.
Really quick, what are the square roots of 4?
2.
2 is a square root of 4, since 2 squared is equal to 4. Are there any other square roots of 4? Negative 2. Negative 2 is a square root of 4, since negative 2 squared is equal to 4.
Yeah.
Right? Negative 2 times negative 2 is 4? Okay, so that's what we mean. X is said to be a square root of b, provided that x squared is equal to b. For any positive real number b, there exists 2 square roots, one positive and one negative, denoted by the positive square root of b and the negative square root of b. So when we talk about the square roots of 4, there's 2 square roots of 4. There's the positive square root of 4, and there's the negative square root of 4, which was positive 2 and negative 2. Those are the 2 square roots of 4. Okay. Another example, I guess. What are the square roots of 16? The square roots of 16 are positive square root of 16 and negative square roots of 16, which are the same thing as positive 4 and negative 4, right? Good? Now, it is very important for you to note that when I write the square root of 16, is this equal to positive 4 or negative 4 or both or what?
Both.
It's equal to positive 4 or negative 4, right? Plus or minus 4 like that? No! This is another place where students get confused. The square root of 16 is always and forever just 4. So let's not get confused going back and forth with these. 16 has 2 square roots. We represent the 2 square roots of 16 as plus square root of 16 and minus square root of 16. But this part of the term is always and forever 4. This part of the term is always and forever 4.
Why is it
So when you have a square root function and you plug in a number, it always spits out a positive value when we're talking about the real numbers.
Why? Why is negative 16 square root 4? Because you just
Look at our definition here for how we set it up. We said that the square roots of b are plus that symbol b and minus that symbol b, where this is a negative root and this is a positive square root.
Yep.
So this part right here always spits out a positive number. And that part always spits out a positive number.
spits out a negative.
It's
Well,
like
the negative makes it negative, but this part right here is always positive.
Yeah.
So then that negative sign is what makes it negative.
Yeah.
So when I write square root of 16, that's 4. If I write negative square root of 16, that's negative 4.
You have to write negative square root of 16 to do square root of 16.
To write the negative square root of 16, I have to write negative square root of 16. You put a negative sign there if you're going to talk about its negative square root, and you put a positive sign there if you're going to talk about its positive square root, because it has 2 square roots.
And if there's no.
But the square root of 16 can still be negative 4 because negative 4 has negative 4 at 16. So it's still going to be negative
4 is a square root of 16. That is correct.
Negative 4 is also square root of 16.
It's bad verbiage that we just read this as a square root of 16. The square root of 16 is the way that we read that, which is bad verbiage. If we were to be more precise, we would read this as the positive square root of 16. So don't get confused. This always spits out a positive number. 16 has 2 square roots. Positive 4 and negative 4.
So that's just
The 2 square roots of 16 are plus or minus square root of 16. So don't get confused in that terminology. And you've solved problems like this 100 times. You said something like, if x squared is equal to 16, then x is equal to plus or minus the square root of 16.
yeah.
But just by itself, square root of 16, that is always and forever just 4. It can never spit out negative 4. And that's one place that students sometimes get confused.
Yeah.
Because you say the same thing, and it means 2 different things. So yes, 16 has 2 square roots. The square roots of 16 are 4 and negative 4. When you see that symbol, square root 16, that's always and forever just 4, never negative 4. If we want negative 4 there, we have to put a negative sign out front.
Okay.
Make sense? Okay.
No.
Alright, because that's a weird one with square roots.
Mm-hmm.
It's like the absolute value of a negative number. Always throw students off. A square root only ever spitting out one number. Throw students off. Okay. Note. Okay. Emphasizing the point once again, this time with 81. No. Square root of 81 means the positive square root of 81, namely 9. So square root of 81 is equal to 9. Negative square root of 81 is equal to negative 9. Alright. I think we got that. Now, so notice what we said up here. We said that if b were a positive number, then it has 2 square roots. Right?
Mm-hmm.
For example, if you pick your positive number 9, its 2 square roots are plus 3 and negative 3. So for any positive number, you have 2 square roots. What about 0? If a is equal to 0, then how many square roots are there? What squared gives me 0?
0.
If I know that x squared is equal to 0, what does x have to equal?
0.
0. X squared, that's the same thing as x times x, right?
Mm-hmm.
And you might remember way, way back, we already proved that if the product of 2 numbers is equal to 0, one of those 2 numbers has to be 0. So either x is 0 or x is 0.
Hard one.
So x is 0. And it's its only square root.
Are you sure? You sure
No.
it's 0?
I'm just seeing what I can get you guys to buy.
Oh, okay.
Practicing to be a salesman.
Really?
Alright. So we handled, if a was a positive number, it has 2 square roots. If a is 0, it has 1 square root. What about if a is a negative number? How many square roots does it have?
2.
2? What do you think?
It's gonna be 1, but it should be 2.
It's going to be 1, but it should be 2?
Yeah,
1, 2. How many square roots of a negative number? Alright, here's what we're going to prove. That if a is a real number and a is less than 0, so it's a negative number. You with me so far?
Yeah.
Then a has no square roots in R. For example, what times what gives you negative 1? If I know that x squared is equal to negative 1, what times what gives me negative 1?
1, I.
Well, real numbers.
Yeah, that's what I.
No I.
Yeah, that's fine. That's
No I. Alright. So there isn't a real number that satisfies this, and we're going to prove that.
Okay.
So if a is a real number and a is less than 0, then a has no square roots in R. There's no real number such that I can square it and get a. That's what we're proving. Okay, so let's prove that. So let a be any real number such that a is less than 0. And assume by way of contradiction, so we're going to set up a bad worldview and show that leads to something impossible. So assume by way of contradiction that a has a square root, call it x. So let's pretend that a does have a square root, and we're going to call it x. We're going to show that that implies a is positive, but we know that a is negative. Contradiction. So that's impossible.
It's true.
That's big picture what we're doing. Does that make sense?
Yep.
Okay. So, assume a has a square root, we'll call it x. Since x is the square root of a, then I know that x squared equals a, right? So then x squared equals a, and I know that x is either greater than 0 or less than 0. It has to be a positive number or a negative number, right? Why can't it be 0? If x was 0, what would a be? 0. Is a 0?
No.
No. So x isn't 0. So whatever x is, it has to be a positive number or a negative number, right?
That's true.
With me so far?
Mhm.
If x is positive, then what's a positive times a positive?
Positive.
Positive. So if x is greater than 0, then x squared is greater than 0. And remember, x squared is equal to a. That would mean that a is greater than 0. But we know a is less than 0, so that doesn't work. So maybe the square root of a is actually a negative number. Let's check that. Well, if x were a negative number, then x squared, a negative times a negative, is a positive. So if x is negative, x squared is positive. And since x squared is equal to a, then that means a is positive.
Yeah.
So in either case, a is positive. Contradiction. We start with a is a number less than 0. So I know a is less than 0. And I really showed, so I know a is less than 0. I showed you that if a has a square root, then a is greater than 0. But that's impossible. So a can't have a square root. That's what I showed. You follow the logic there?
Yeah, just because you can't take two of the same thing and make a negative out of it, it's impossible.
Right. If I take the same real number and multiply it by itself, it always comes out positive. If I take a positive and multiply it by itself, I get a positive. If I take a negative and multiply it by itself, I get a positive. If I take 0 and multiply it by itself, I get 0. There's no way for me to take a number, multiply it by itself, and get a negative number out of it. It's always either 0 or positive. Okay. Therefore, a has no square root in R. Good? Any questions on any of that? All right, let's jump over here and see what we were doing. I can't see that. Make my camera so dim so I don't die. Okay. And something that we know, because I guess the author noted it. Now, if a is greater than or equal to 0, then the square root of a squared just gives you a.
Hey, that's
A. Bunch of bad markers. Okay, so now I'm going to do a quick proof for you that the square root of x squared is equal to the absolute value of x. And this is actually sometimes how this is defined. Or at the very least, it's a very useful substitution in a lot of problems. So the square root of x squared and the absolute value of x are the same thing. That's what we're going to prove. So let x be any real number, and observe that either x is greater than 0, or x is equal to 0, or x is less than 0. One of those three cases has to be true. Right? And I may show that in either one of those three cases, it's still the case that the square root of x squared is equal to the absolute value of x. So let's take it one case at a time. If x is greater than 0, then the square root of x squared is just
Positive.
remember, let's say it that way. If x is greater than 0, then the positive square root of x squared is just x.
Yeah.
Look, what are the two, if we have x squared, what are its square roots?
X and X. X and negative X.
X and negative x. Take that, multiply it by itself, I get that. Take that, multiply it by itself, I get that.
Yeah.
So the square root of x squared spits out its positive root. If x is greater than 0, in other words, if x is positive, this one's its positive root.
Yeah.
So the square root of x squared is just x. It's positive root.
Yep.
You with me? And what's the absolute value of x if x is greater than 0?
Just itself.
It's just x. So those are the same. Okay, next case. What about if x is 0? If x is 0, then let's see, what's 0 squared?
13.
What's 0 squared? 0. What's the square root of 0? 0. And what's the absolute value of 0? 0. So that is still equal to that. Now let's do the next case. What about if x is less than 0? If x is less than 0, then what's the positive square root of x squared? Negative x. Remember that if we have our number line, here's 0. If x is somewhere over here, then negative x is over here, right?
Yes.
So, the positive square root of x squared is which one of these two numbers? Negative x. It's the positive number. So the positive square root of x squared is negative x, since x is a negative number. So a negative number is a positive number, right?
Oh, yeah.
Furthermore, the absolute value of a negative number is negative that negative number. And so it's still equal to the absolute value of x.
Okay.
You follow that? Is that a bit much? All right. Okay, so let's do some quick examples. What's the square root of negative 5 squared? Negative 5. It's the positive root. Right? We're looking at that case. This case is right here. Which is also the same thing as the absolute value of negative 5.
Which is 5.
Which is just 5. Right. But I just want to show that that and that were the same thing in an example. Make sense? Okay, now let's look at this one. What's the square root of 189 squared? 13?
13.
So 13 squared is equal to 169.
No, that's 14.
14 squared has to end in a 6.
It's not 15. 14.5.
Take a step back from the problem. The square root of 189 squared is 189.
I was so confused. I was like,
189, which is the same thing as the absolute value of 189.
That makes sense.
Yeah, don't overthink it. You get used to, when you see a square root and you see something that looks like, it could be a perfect square, your brain naturally wants to do it. Stop, think about the problem, don't let those bad habits make you screw up the mathematics, because it's hard to break those habits. It's one of the problems with the way you're currently taught how to do algebra. They give you these drill sheets that just give you a bunch of perfect squares that you calculate the square root of, and so your brain can't even help it, you're so used to doing it. Instead of giving you problems that make you stop and think about definitions. Okay, so last thing we'll talk about is a perfect square. What's a perfect square? You already have some good intuition for what a perfect square is, but we'll read the definition. A rational number is a perfect square provided that it is a square of another rational number. Let's try an example. Oh, we have some right here. 169 over 25, that's a perfect square. Why? Because that is 13 over 5 squared. Since it is a rational number squared, then we call it a perfect square. So a rational number, namely this thing, is a perfect square provided that it is a square of another rational number. Here's the other rational number that it's the square of. Make sense? Now we also have the notion of a perfect square applying to a monomial. A monomial is a perfect square if I can represent it as a square of a monomial. So this monomial is a perfect square because I can represent that as this monomial squared. Now we take it one step further. We say that a quotient of two monomials is a perfect square, provided that it can be represented as the square of a quotient of two monomials. Make pretty good sense there?
Yeah.
Okay, so that will be it for new material that we cover this week. We can do a couple exercises until you feel content. I think we covered some exercises. Did we not even get to a new set of exercises? Nope, we didn't. So I lied to you. Okay, so never mind. So, we'll end it there. Unless you want to talk about the size of these things. You want that recorded? Do you still want to talk about comparing the size of the naturals to the size of the integers to the size of the reals?
Yeah,
I
why
wanna
don't
see
we
the
do
size
that?
of the reals, like how you put that as a function.
You want to see that? Do you want it recorded?
Sure. Either one on this out.
Kind of torn. It doesn't really contribute to the class. I'm not going to do it.
Okay.
But, yeah, we'll show it.